Hello, everyone. Welcome to another OpenShift Commons community call. Today is Wednesday, November 22nd, and I am going to skip the announcements and we'll just go straight into the highlight of today, which is talking about MetalLB and load balancing and Kubernetes. And thank you, Federico, for joining us today. Could you please introduce yourself, and I'll go ahead and hand it off to you.
Yeah. So I'm Federico. I work for Red Hat. I've been here for almost 5 years now, and I'm part of this networking team in charge of the telco side of OpenShift. We try to make the OpenShift and Kubernetes platform in general suitable for telco workloads. And I've been maintaining and leading the MetalLB project for the past couple of years.
Thank you. I'm really excited about this presentation. Yeah, I know a lot of the community members on here are as well, a lot of edge and telco interest. So thank you again for being here.
Do you want me to start, or?
Yes, please. And we'll just have questions in the chat. And if anybody wants to jump in, let us know and feel free to ask any questions. And as Tomasz mentions in the chat, vSphere users as well. So thanks for mentioning that. Yes, please.
Okay, so basically this is a reiteration of what I did internally in the latest Red Hat Networking Summit. Yeah, this is basically me. I did not focus on particular features in the initial years at Red Hat. I contributed here and there in networking-related projects, but lately my focus is mainly MetalLB. I will start with something that is probably trivial to any of us, which is what a Kubernetes service is. Kubernetes service is a way to load balance our workloads across different our requests across different endpoints with the TCP, UDP, or even HTTP. And the service is the Kubernetes abstraction that allows us to balance a virtual IP across a different set of pods. The virtual IP, which is the cluster IP, is accessible from inside the cluster. So it's a way to load balancer the traffic from one pod living into the cluster to a set of other pods living into the cluster. It's more or less like that. We have ports, IP families, but that's the general idea. But what if our application needs to be exposed to the external world? And what if we need some particular protocol and not HTTP or L7? So one of the ways that Kubernetes allows to do that is by using what they call services of type load balancer. And this is the definition taken from the Kubernetes documentation. A service of type load balancer exposes the service using a cloud provider's load balancer. And then it says that the node port and cluster IP services are created, blah, blah, blah. But the emphasis here, the thing I want to stress on is the cloud provider. So what happens when we create a service of type load balancer? We get an external IP that is the first thing that comes from the cloud provider. We get an IP available from outside to our service, and then the second part that we get from the cluster provider, the cloud provider, is the load balancing. So the cloud provider's infrastructure is in charge of driving the traffic directed to that virtual IP, the external IP assigned to our load balancer, to all the nodes. Once the traffic gets to the node, the work of the load balancer is finished. And this is particularly important to understand how MetalLB works. So the only simple, not so simple purpose of the external load balancer is to have the traffic reach those nodes. And in case of cloud providers, it's a real network load balancer. So a load balancer service provides a couple of things. One is a stable IP that allows us to reach our applications. And second thing, the load balancing across the different nodes. Now let's see what happens when we move to bare metal. If we don't have the cloud provider infrastructure, the first thing that happens is that no one is giving us that IP, because we don't have control on the network infrastructure. We don't have this automation that gives us the external IP that we can pin to a DNS entry or give to our users. And the second problem is, even if we had an IP, who is routing the traffic to all the other nodes so that the primary CNI can do its part. And these two particular problems, assigning the IP and routing the traffic, are exactly what MetalLB aims to solve. MetalLB is a community project under the CNCF umbrella. It was donated more or less when I started maintaining it a couple of years ago. And it was the first implementation of load balancer services on bare metal. So the first disappointing thing I found when I started looking into MetalLB is the fact that MetalLB, despite the name, MetalLB is not a real load balancer. It's not a real load balancer in the sense that it's not doing connection multiplexing and handling the connection itself. But that doesn't mean that it's useless. Like, it's used a lot, so it must be doing something. And let's keep in mind that those two issues I spoke about before, and let's have a look at how MetalLB is able to solve those problems in an elegant way. So the first item is address assignment, and this is probably the most boring and less networky part, but still not so simple. It's a normal Kubernetes controller. It listens for services of type load balancer, gives them an IP, and then takes the IP back when they die, so that IP can be reused for another service. But we are not on the cloud environment. We are not a cloud provider, so which IPs are we talking about? The only one that knows what IPs are available in the current infrastructure is the cluster administrator. So in order to make those IPs available to MetalLB, there is one resource, IP address pool, where you can define your range of IPs. You can have IPv4, IPv6 as a range or as a CIDR. You can have multiple instances of this object. And we can have extra features to say, from a given service, I want exactly that IP, or I want an IP exactly from that IP address pool among all the ones that we have configured. And we also have namespace selectors to say this set of pools, and this is particularly useful in case of multi-tenancy. So you can say, I have this set of IPs and I want to assign them only to tenant A because of reasons. And that's how we do that with the namespace selector and with the service selector. So a couple of things about address allocation. MetalLB's spirit was and has always been with simplicity in its heart. And so a simple configuration with no configuration is the default, is meant to be the most easy to configure and the easiest one. So if you don't specify any selector, that means that the address pool will be applied to all the services. If you have a service that asks for an IP, but you don't have it selected, then the service will not get that IP. And yeah, this is more or less the same thing. We can also, if you have different ports, you can share the same IP among different services, and we support dual stack services as well. So your IP address pool has to have ranges of the two different families, but then MetalLB will associate the two different IPs to the service. The second part, which is the networky part, is the address advertisement. So remember what I discussed in the beginning. We have the address, we have a client that wants to access that address, and in some way, we need to attract the traffic directed to that virtual IP towards our nodes. And another thing to remember is the external traffic policy that is supported by MetalLB. So you can have a cluster, the external traffic policy cluster, when the service is announced by all the nodes, and the traffic might traverse from one node to another to reach a pod that is living on a different node compared to the one where the traffic landed. Whereas with local traffic policy, MetalLB will be smart enough to announce the traffic only from those nodes where an endpoint pod is living. And there are two ways to announce the traffic, to announce the virtual IP. One is L2, which is simple, doesn't require a very complex network infrastructure, and expect more or less the client and the cluster to live in the same local network, or to have a very specialized network infrastructure that allows the traffic to get there. I will expand this a bit later. Or BGP mode. BGP is the more fancy, but requires a good infrastructure with BGP-enabled routers. Let's talk about L2 mode first. And L2 work more or less like keep alive D. So to intercept the ARP request reaching each node, MetalLB elects for each virtual IP in a fair way. For each virtual IP elects a leader that is in charge of announcing the service, and then only that replies to the ARP request with the MAC address of the interface it received the request from. So then the client knows that node 2 is the one, or the MAC of the interface of node 2 is the one that to reach the service, and then the traffic flows in. The traffic goes to the node, the CNI does the rest. What happens when a node dies? The failover kicks in, a new node is elected, a gratuitous ARP is sent out, and the client is able to reach the new node again. So there is no real load balancing in this case. It's more like an implementation of services of type load balancer, but might suit some cases, specifically like if you don't have a BGP router in your home lab and something like that. It's slightly similar to keep alive D. We don't assign the IP to the interface, and the configuration is pretty simple. Just the IP address pool and the L2 advertisement, and that's it. Then, if you have your laptop and your home lab, you'll be able to reach the service running into the cluster. And of course, we have pool selector. So if you have a bunch of IPs and you want to advertise only a subset of those services from via L2, this is how to. The failover time is not fast. So like it's I don't remember, but it's in a matter of seconds. If you want something faster, then BGP is the way. I will expand that later. So where I was. We have node selectors. This was asked by a few users that were trying to expose the service on. We're trying to expose the service only from subnodes, because only those nodes were exposed to a particular subnet. And with node selector, you can limit the number of nodes where the IP is advertised from. And we have interfaces selector, because by default MetalLB sends to ARP requests from all the interfaces, but there are some tricky combinations with the bonding and bridges. So it might be that the reply goes on the wrong interface, because MetalLB receives the ARP from two different interfaces. So interface selector is the way to try to solve this problem. And this more or less is the same that I said. So it's not really load balancing, but it's a way to expose the virtual IP in the less intrusive way in your network. Next item is BGP mode. So by the definition of BGP, this is taken from the RFC, is the primary function of a BGP speaking system is to exchange network reachability information with other BGP systems. So this is exactly what we are looking for. We want to advertise the reachability of our virtual IPs to other networks so that the traffic can reach the nodes, and then the CNI does the rest. So in BGP mode, each node acts as a mini router. It establishes a BGP session with the configurer routers. The BGP session is established up front, and MetalLB must be instructed of the presence of the router. Then MetalLB will advertise the network reachability of the service, saying, hey, if you want to reach the virtual IP, then you can have node 1 as the next stop or node 2 as the next stop. And then the router will know about those. And in this case, it will be real load balancing in charge. The component in charge of the real load balancing will be the router. It's ECMP routes, so it's active. It depends on the router. And this scenario can be more complex. You can have multiple routers, and you can have a high hierarchy of routers. And yeah, this is how we configure that. You still need the IP address pool to do the IP assignment. And then there is the BGP peer that represents the BGP session with an external router. So you need to define the address, the autonomous system number, the port, and a few other parameters of the session. And again, the BGP advertisement declares our intention to advertise a given the IP coming from a given IP address pool via BGP. And an empty advertisement means I want to advertise all my services coming from MetalLB via BGP. We added some extra features over the time, node selectors. So if only a subset of your nodes are able to reach a given BGP peer, you can use node selectors to avoid wasting resources in trying to connect to something that you will never connect to. We have communities and local preference. Communities are properties that you can associate to routes. Local preference is kind of a hierarchy of different importance of the various IPs. MetalLB also supports BFD. The BGP maximum failover detection is 3 seconds. BFD is way faster than that. It goes below the second in a very effective way. And by associating a BFD profile to the BGP peer, MetalLB will automatically establish also BFD session that it will bring down the BGP session as soon as the BFD session breaks. That will allow faster failover detection. So we have a few extra parameters again that were added over time. We have the IP address pool selector, so you can choose to advertise via this BGP advertisement only a subset of the services. We have node selector, the same as L2 more or less. So here is still active, but you can drive the number of nodes that are announcing the given service. And you can choose also, and this is useful for if you have multiple networks and you want to segregate the traffic in some way by using the IP address pool selector and the peers, you can advertise your class of services only to a subset of the BGP peers. And yeah, this is more or less what I said. if you don't have a selector, you will advertise everything, and all the BGP advertisements applied to the same IP address pools are combined together. So BGP is more or less real load balancing. Of course, it requires an effort on the infra side that it's not required on L2. Despite the fact that it's a real router, we are refusing incoming routes so far. That might change in the future because those might break in the cluster, and they defeat the purpose of MetalLB, which is only advertising the services. And we support iBGP and eBGP single and multi-hop scenarios. And things can be mixed together, so we can have one simple MetalLB configuration with the defaults, just the pools, and L2, an empty L2 advertisement, and it will work on your machine. People are using it together with Kind, for example, to do their tests. But we can also have more complex configurations achieved by mixing everything together, and those were to follow some big enterprise users. For example, we can have the same service advertised by both L2 and BGP. We can advertise via L2, but only from a subset of the nodes that are connected to a given subnet. Or we can announce the node to a given peer, but only from a subset of the nodes, and so on. So now I will talk briefly about the architecture. There are two classes of pods. One is what is called controller. The controller runs in single instance and is, as I said already, a boring Kubernetes controller. It listens for services, it listens for available IPs, and performs the allocation. We have the speaker. It runs one per node that is in charge of the networking part, so the advertisement of the service outside of the cluster. In case of L2, everything lives inside of the same process. It's a Go binary with an implementation of ARP inside of it, and it listens for requests and replies, does the election, and so on. The BGP mode comes in two modes. One is the native mode that was there when I started maintaining MetalLB. It's a subset of the BGP spec implemented in Go, and again listens for services and the configuration and does the announcement. And then we have what we added a couple of years ago, which is an FRR-based BGP implementation. So FRR is a well-known component. Its roots come from Quagga, and it's a Linux suite that implements a variety of projects, including PFD and BGP. So in FRR mode, we are running FRR inside each node, basically a virtual router on each Kubernetes node cluster. And our speaker container now will listen from the Kubernetes API in terms of services plus configuration, and renders the FRR configuration and reloads it. So FRR, which is a bottle-driven BGP implementation, is in charge of doing the actual work for us. Finally, we implemented a MetalLB operator that is an alternative from the manifest and from the Helm chart to deploy MetalLB. It's available as a community operator or in the Red Hat marketplace. Yeah, this is quite old, so you might not be interested into this. Wrapping up, there are two major tasks when you want to solve or implement a service of type load balancer. One is IP allocation, and the other one is IP advertisement. We have L2, which supports failover, but not real load balancing, and BGP that requires BGP-aware routers. So with that, I'm finished my presentation, and I'm happy to discuss about MetalLB.
Thank you. We have some great questions. in the chat. Let's see. First is from David. Does MetalLB function like an infra node, or is it completely separate?
Yeah, I think that was clear in the presentation. MetalLB runs as part of the cluster. It is expected to run at least the speaker node, the speaker pod. It is expected to run from every node that is able to reach traffic towards the virtual IP.
Thank you. I know we have a lot of questions on between what's infra and what's not. What about, is this horizontal auto-scaling?
Can you expand the question a bit, because I'm not sure I understood it.
So this goes back to the middle of your presentation, Dwayne.
No, I see the question, but if Dwayne can expand a bit on the question, because I'm not sure I understood the question.
Dwayne, would you like to jump in, or?
Hello. Yeah. So, I was reading something from Datadog, and they were talking about the importance of horizontal pod auto-scaling. And I was just trying to see, was this a similar thing, or did MetalLB have this capability? Because it was talking about, similar things where you could do with external IP addresses to make more pods come up and go down and scale, come in a different type of load balance. So I was just trying to see what is similar.
Yeah, I think I understood the question. Like, MetalLB doesn't do anything like that per se, and I don't think we have a way to understand what is the volume of the traffic in order to provide some data to the application to scale up or scale down their pods. So yeah, we are not offering anything like that automatically, because MetalLB, once the traffic announcement is done, MetalLB doesn't even see the traffic. So that part would probably more suitable for the primary CNI to have some knobs that says, hey, your virtual IP is reaching, like, getting a lot of traffic, try to scale up or scale down, or something like that. Or in general, you can have something else that observe the amount of CPU. Maybe there are, like, that's how TIDA and all. I'm not familiar with those, but maybe that's how those works already.
Thank you. So next question, Piotr, would you like to jump in?
Yeah, I read about the failover time, and I don't remember the figures. Again, L2 is not known to be super fast because it requires some. We have this gossip protocol among the nodes that allow one speaker to understand that another died, and that is where the majority of our time goes, because after that everything moves faster. But like, understanding when a node goes down might take some time. So I understand that not everywhere you can have BGP, but that's how it is today. MetalLB and Origin. We've seen, okay, I'm trying to read the.
I can describe it if you
Yeah.
want. Okay, so I'm just trying to see where to start, but essentially, maybe let's start with appreciation the fact that indeed your technology is being used heavily in telco companies, which we learned hard way. For us, but not for you. I mean, it looked like it's indeed great technology. So really what I'm after is trying to understand what and if are there any best practices for application developers who are deploying applications on OpenShift, and they kind of standardize towards services and routes, right? OpenShift constructs versus MetalLB, right? So how to make sure that your application is, can operate with both. Right now, our understanding either, but not necessarily both, right? So,
okay, I'm not super familiar with HA proxy and like ingress controllers in general, but my understanding is that you can have the ingress controller backed up by a service of type load balancer that is fed by MetalLB, and that is for L7 stuff. Then you might have a different virtual IP where you want to have your custom protocols or stuff like that that are running without having to go through a separate proxy. This is my understanding, and again, we might want to pull in somebody from the ingress controller side to validate this, because like I know that a lot of people are using MetalLB in combination with those, with traffic, HA proxy, and Nginx, and my understanding again is you get the load balancer service from MetalLB, or that controller just creates the service of type load balancer, and then all the magic is done by the other component.
Yeah, sure. Well, indeed, happy to have a follow-up on that.
Yeah, I don't know if like Karina, you might pull in somebody else from the. Okay. Instead of BGP, could we utilize OSPF? So one of the advantages of having brought FRR as a backend of MetalLB opened a lot of new features. BFD, for example, was one of the things that were asked a lot by a lot of users and would have been hard to implement it by ourselves in Go, or like not hard, maybe even fun, but having something that had already it on board was easier for us. So this is to say that FRR supports OSPF. We didn't see much requests from both upstream users and users of OpenShift to the protocol. But what it would take is taking figuring out some API and translating that to the corresponding FRR configuration. And the last question is, MetalLB always needs extract IP? Yes, the answer is yes, because if it uses the host IP, then you might, especially in case of BGP, you might confuse the network and have the same IP exposed by two different nodes. And if that IP is the IP of the primary interface, you might even risk to break the cluster.
Are there any other questions while we have Federico here? I put the link to the website for the project in the chat, and I'm sure David or Dwayne has already put those in the note because you two are super fast.
A couple of other things I want to mention is we constantly monitor the issues on the GitHub project. So if you have some troubles, that's the first place to write on. There is also the MetalLB channel on the Kubernetes Slack. It's pretty active, and I see like users helping among themselves. But we always keep an eye on there, and we try to help as much as we can.
No, you're always super fast. Oh, good question, Lenka. You mentioned users, but what about contributors? What are the best ways to start contributing to MetalLB?
Oh, that is a question I like a lot. So we try to be good maintainers. So there are a bunch of issues that are labeled as good first issue, help wanted. There are contribution guidelines. There is a documentation on how to spin up a development environment based on kind. We have all sorts of CI for L2, BGP, single and dual stack that should give us enough confidence that nothing is breaking so drastically. At least there are still always corner cases, but at least the regular stuff is known to work. And of course, there is this MetalLB dev channel still on the Kubernetes Slack. So if you want to ask questions, And if you want to contribute something that is not listed on the issues, I strongly suggest to file an issue first, so we can engage the discussion to understand if the feature is meaningful or not, or if there is another way to solve the same issue without changing anything or more adherent with the project stack. But contributors are always welcome, and there is a good turnover of contributors in MetalLB, I think. Even casual ones that can fix the CI or improve the CI or some features or some bugs and so on.
Yes, thank you very much. All right. So I know, yes, thank you again for being with us. And if there's any last questions, I know it's going to be a long weekend for some of us, and the others get a nice break.
I strongly envy you because I won't get it.
It'll be at least quiet for you.
Yeah.
Yeah. Okay. Well, thank you, everybody, and we'll see you in the Common Slack or in the MetalLB Slack on the Kubernetes Slack. But we'll see you next week, same time, next Wednesday. See you all soon. Thank you.
Thank you.